We have been investigating different classes of lipids and exploring how different attachments can impact their structures and characteristics. At the very end of analyzing glycolipids, we saw that these glycosphingolipids are mostly observed on the exoplasmic leaflet of the plasma membrane, starting our expedition into looking at the lipid membrane as a whole and analyzing its characteristics. To continue learning more about the factors that influence the dynamic properties of lipid bilayers in the cell, we are going to have to refer back to general chemistry. Intermolecular forces are the forces between molecules or ions and are dependent on the different functional groups or charges the molecules or atoms have, such as ion-dipole, dipole-dipole hydrogen bonding, and more. But the important forces that's going to help us learn more about the fluidity and rigidity of bilayers are dispersion forces. London dispersion forces are exhibited in all molecules, yet are only considered a drastic player when comparing the interactions between two nonpolar molecules. Dispersion forces are dependent on the natural flow of electrons within atoms. When the two groups come in close proximity to one another, one group's natural flow of electrons pushes the electrons of the adjacent group, causing a momentary dipole and separation of charges within both molecules, causing that weak attraction force. Since this instantaneous dipole within the nonpolar molecule is dependent on the distance and surface area the two molecules can interact between, longer, less branched carbon chains will have stronger London dispersion forces between each other, which will also result in a higher boiling point. This is important to our lipid bilayers. When analyzing the lipid interactions, longer saturated carbon chains in the tails of lipids will have stronger forces between each other than lipids that contain unsaturated chains, all because of dispersion forces. The unsaturated carbon chains will have compromised surface area interactions, since the double bond places a kink in the chain. The more interactions lipids have with their adjacent neighbors will result in higher order, or packing, of the lipids in the membrane, whereas with unsaturated chains, the movement of the lipids would be more fluid since the attraction between them is limited. This is where we start understanding these bilayers have fluid characteristics which are dependent on the concentrations of lipids they are composed of. Yet there are other factors that influence the balance between rigidity and fluidity, such as temperature. Temperature will increase kinetic movement of lipids, resulting in a drastic increase of fluidity, yet a decrease of temperature will have an opposite impact, restricting movement, both rotationally and laterally, resulting in a more rigid membrane. Both extremes are not sustainable for a bilayer within cells, and can result in the bilayers breaking or disassembling. There needs to be a way to balance and regulate fluidity, where we introduce a new class of lipids that look nothing like what we have seen before, steroids, which are characterized by a distinct 4-fused ring structure consisting of 3 cyclohexanes and 1 cyclopentane. And unlike fatty acids and different membrane lipids, they do not spontaneously form bilayers, yet are lipophilic, which means that they easily combine or dissolve in lipids. This is a very big and important class of biochemical molecules, ranging as precursors of hormones, vitamins, and more. Yet since we are focusing on membrane dynamics, I want to restrict our focus on cholesterol, a type of steroid that is very influential to membrane fluidity. Sterols, which are a subclass of steroids that cholesterols belong to, is classified by a hydroxyl group on the 3rd carbon position of the A ring. Cholesterol has additional branching and methylation, yet the hydroxyl group is essential to how it sits in the lipid bilayer. With the OH group, cholesterol is now amphipathic. The polar OH aligns with the polar head groups of adjacent lipids, and the ring structure aligns with the tails, allowing it to sit within the membrane. But how does it impact the fluidity of the rest of the membrane? Let's analyze its influence to packing first. Highly packed lipids with cholesterol are more fluid since the sterol sits in between lipids, acting as spacers, limiting dispersion interactions that we talked about earlier. Whereas with more fluid lipids, cholesterol helps limit lateral diffusion, resulting in more rigidity in the bilayer. More or less, cholesterol helps create a balancing act between rigidity and fluidity. ranging temperatures with cholesterol. At higher temperatures, the membrane would be less fluid, and at lower temperatures, they would be more fluid, allowing the lipid bilayers to respond more slightly to temperature changes, all because of cholesterol incorporating itself in the membrane. Now that we know the root impact of cholesterol and lipid structures, let's dive into some specific cases where ranging cholesterol levels can further assist cellular function. First, depending on the organelle or membrane, the ranging concentrations of cholesterol and types of lipids fluctuate depending on the need and function of the organelle. For example, the mitochondria has less cholesterol than the nuclear membranes, where lysosomes have drastically more cholesterol than the plasma membrane. Also, within those bilayers, there are microdomains, usually referred to as lipid rafts, where isolated segments of increased concentrations of sphingolipids, glycosphingolipids, and cholesterol create an extremely packed floating segment within the bilayer, which can impact migration of other components within the bilayer. During our continued exploration of biochemistry of lipid bilayers, we're definitely going to return to some of these principles. I truly hope this video helps gain a holistic understanding of cholesterol and the ever-moving fluidity of lipid bilayers. All these pages and more can be downloaded for free on my website to help with your studies. Wishing you all the best and have a great day.